Look down at any major city at night, and you'll see a world running on an invisible force. To actually control this grid, humanity first had to translate that unseen power into strict mathematics. To understand how we map that power, we have to start at the absolute bottom of physical reality, the subatomic level. Here we find the atom. Specifically, we are looking for the electron sitting on the outer shell, the mobile carrier of negative charge. Isolating this single particle is our starting point, but a lone electron is far too small to perform any real engineering work. You cannot design a hydroelectric dam by counting individual water droplets. Engineers require a macroscopic unit of measurement to build functional machines. This diagram shows the coulomb, represented by the letter Q. It takes that single subatomic charge and scales it up into a massive, standardized cluster. To be exact, 1 coulomb is equal to roughly 6 × 10 to the 18th power, or 6 quintillion, electrons. Establishing this specific number provides a reliable baseline. We now have a fixed quantity that behaves predictably in our mathematical formulas. Defining this massive bundle of charge bridges quantum physics and human engineering, giving us a tangible material we can push through a wire. Having defined the raw material, the very next crucial step is tracking its motion and speed over time. This diagram visualizes current, or I, as a rate of flow. When exactly 1 coulomb of charge passes a specific checkpoint in 1 second, that flow rate equals 1 ampere. But here we run into a historical contradiction. In physical reality, these negatively charged electrons are repelled by the negative terminal and flow toward the positive one. Electricity was harnessed long before the electron was discovered, leading early scientists to make a backward assumption about the direction of the flow. As this diagram shows, that guess gave us the unbreakable rule of conventional current. All standard electrical math dictates that current flows from positive to negative, the opposite direction of the actual electrons. While physically backward, understanding this quirk is an absolute prerequisite for successfully navigating the mathematics of circuits. Subatomic particles do not move through a wire spontaneously. They require an external force to push them. This animation illustrates potential difference, better known as voltage. It is the invisible electrical pressure driving the circuit, established by the amount of work done to move a unit of charge. Conceptually, 1 volt is the potential difference created when exactly 1 joule of work is used to move 1 coulomb of charge from one point to another. To track these invisible forces in physical reality, engineers rely on diagnostic tools to monitor the system. This is an ammeter. To count the physical flow of charge, it must be wired directly in series, sitting right inside the circuit path. By contrast, the voltmeter is placed in parallel to measure the pressure difference across components, completing the toolkit needed to control the power. As electrical systems grew more complex, drawing physical wires, batteries, and meters became impossible for engineers to manage. The solution was the electrical schematic, a translation of chaotic physical reality into clean geometric shorthand. In this translation, messy, tangled wires and glowing bulbs become perfectly straight lines and standardized zigzag symbols. This symbol-based grid became a universal language, allowing a circuit designed in one country to be perfectly understood in another. Every line and symbol on this schematic functions as a precise mathematical map, dictated by the foundational formulas for coulombs, amps, and volts. By stepping up from the invisible electron, quantifying its flow, measuring its pressure, and designing a universal symbolic language, humanity successfully tamed the physics of electricity to build the modern world.